This set of notes will be covering basic information on the chemical reactions unit. So this is sort of an introduction to basic concepts in chemical reactions. The first thing that we need to talk about is what a chemical reaction is. And so generally speaking, what a chemical reaction is when you have two substances and you mix them together and they kind of change to make new things, new substances. All right, and what this change involves is rearranging atoms and forming new bonds, breaking old bonds and forming new bonds, so that the connectivity between the atoms is different when you end up at the end. And so when we do a law of conservation, when we do a chemical reaction, it follows the law of conservation of matter, which says that matter can neither be created nor destroyed. And the consequences of that is that however many atoms that we start with, we have the same atoms in the end. They're just rearranged, and new bonds are formed between them. Now, I'll say there is one exception to this, and that has to do with nuclear chemical reactions, where the nucleus of an atom is actually rearranged, and an atom can split to be multiple other atoms or various other things. However, I'll say in this class, we don't really talk about nuclear reactions that much. So for all intents and purposes, in this class, the number of atoms that you have at the beginning of a chemical reaction is the same as the number of atoms that you have at the end. All that's happened is that bonds have broken between some atoms and new bonds have formed. As a bit of a review, we have these 5 signs that a chemical change has happened or that a chemical reaction has occurred. One of them is color change. You see here with the banana or the rusting on the car. That kind of indicates that a chemical reaction has happened. Also, we can have bubbles or gas released. That happens in the case, a lot of times you'll see in a chemical reaction. Here we use an example of Alka-Seltzer, but if you mix, say, hydrochloric acid and zinc metal or magnesium metal, things like that, a gas will be produced. So if you ever see any bubbling or fizzing, that might be a good sign that a chemical reaction has happened. However, there is a bit of an exception here because there are some things where you'll see bubbling occur, but it's not a chemical reaction. For instance, if you're boiling water, you'll see bubbling there, but that's not a chemical reaction. That's just a physical change that's occurring. The water is going from liquid water into gaseous water, and so it's not a chemical reaction there with something such as boiling, which is a change of state. Also, you might see a color change in times when it's not a chemical reaction either. For instance, if you were to paint over something, painting something changes its color, but it only changes its color by covering it up, and so that's a color change that is also not a chemical reaction. So just be careful. They're rules of thumb, but they're not always the case. The next thing I'm going to talk about is endothermic and exothermic reactions. These aren't terms that we've used before, but I want you to become familiar with them. Endothermic, the prefix endo means that heat is coming in, or it means into, okay, and exo means that it's leaving. And so generally speaking here, if we use the term exothermic, we mean heat is leaving a reaction. If we use the term endothermic, we mean that heat is coming in to a system or coming in to the reaction. Now, something that's confusing about this is that people think, for instance, endothermic means that heat is being brought in a reaction. People think when you hold that it would feel hot because heat's coming in. Now, that's not entirely accurate because that heat that comes in is being used to break bonds and form new bonds, and so the heat isn't going to changing the temperature. So when people say that heat is coming in, they get this misconception that the temperature is going up. That's actually not the case. In fact, as heat is coming in, it's pulling heat in from its environment. So if you're holding something and it's undergoing an endothermic reaction, you're holding it in your hands, it's bringing heat in from your hands. And so if it's removing heat from your hands feel cold. And so endothermic feels cold because heat is entering the system, but it's entering it coming from your hands, and so it feels cold to you. Similarly, exothermic means that heat is leaving a reaction, all right? And if heat is leaving a reaction, it's leaving the reaction and going into, say, your hands if you're holding it. And so exothermic, heat leaving, feels hot to you. Endothermic, heat coming in, feels cold to you. Another sign is light given off. I give you the example here of a fire gives off light, and so we know that a chemical reaction is occurring there. Also, in the case of like glow sticks or those necklaces that you wear at the 4th of July, a chemical reaction occurs there. That's why you have to break them to get the reactants to mix, and then they start going. So that's another one. As a last one here, if you mix two liquids together and you get a solid, that is called a precipitate, and that is a pretty sure sign that a chemical reaction has occurred as well. So precipitates forming is a sign that a chemical reaction has occurred. All right, getting into some other basic representations here and doing a bit of a review. If you see a chemical symbol like this Fe here, Fe, hopefully you know, or you could look at the periodic table and find out that Fe represents iron. Iron is an element, and so chemical symbols we use to represent individual atoms or elements. Something like the C2H6O, that is called a molecular formula or a chemical formula, and we use those to represent entire compounds or entire molecules. As a reminder here, the term molecules, although I'll occasionally use it incorrectly as well, molecules really technically only applies to covalent substances. Otherwise, we call it an ionic compound. So just something to think about there with the word molecules as a review. The new thing that we're talking about here are chemical equations or chemical reactions, which are represented by these chemical equations. And so we're getting bigger and bigger here in terms of the representation. And so you might have seen a few of these floating around in the past. We haven't really discussed these big, long equations that look like this. I've given you here 5 examples of what chemical equations look like. You have things on both sides, and they're used to represent an entire chemical reaction as it occurs. There are a couple parts of the chemical equation. First of all, you have the reactants, which is what you're starting with. Those fall on the left side of the arrow. You also have the products, which fall on the right side of the arrow. All right, and so usually when we write things in a chemical equation, it says the reactants go to the products here, or as an actual example here, if you have H2 and O2 as your reactants, then they form or make H2O. That is your product there. And so in a chemical equation, we use the arrow there to separate the reactants and the products. And I'm going to talk here in just a second about what that arrow sort of means. So we've got these different symbols that come up. The arrow, usually how we read that is we read it as yields. Yields just means that it makes something. And so for instance, back on this slide, I might say hydrogen gas and oxygen gas react together to yield water, or hydrogen and oxygen yield water. All right, so the arrow, oftentimes we read it as yield or yields. And what it means is it's just that the reactants are making the products in the course of the reaction. There are these other arrows that sometimes we see. If it's a double arrow like that, it means that the reaction is reversible. If they're the same size, that means the reaction is reversible and it goes approximately with the same amount of ease in both directions. Sometimes, though, something is reversible and it favors the products, meaning it can go both ways, but it really is a lot easier to make the products from the reactants. Sometimes it's reversible, but it's reactant favored. In this case, it means it's kind of hard to make the products from the reactants, and it's actually a lot easier to go from the products back to the reactants, and so it's reversible, but it favors the reactants in that reversibility. Some other things that we see here, if you see a temperature over the yield sign, what that's going to indicate is the temperature at which the experiment should be done. And so I think about it as like cooking. You say oftentimes like preheat your oven to 400 degrees Fahrenheit or something like that. Although I'll say this is in Celsius usually if it's written over a yield sign. As an alternative, sometimes we'll see this triangle here, this delta. The delta just means that you should heat it lightly. It's an alternative of giving a specific temperature. It says heat lightly, like in a warm water bath. A lot of times what we'll do is we'll use say a beaker full of water, and we'll heat that beaker and we'll put a test tube in it, and the purpose of that is just to make the reaction a little bit warm to help it happen. If you have a chemical sitting over top of the yield sign, that chemical is a catalyst. What a catalyst is it's something that helps get a reaction going. All right, but it's important to say that a catalyst is not a reactant. A catalyst is not used up in the reaction, so it's not a reactant, it's just something that helps. And so an example that I give to help people remember this is, I give the example if I say to my students, if I told you to go outside and dig a hole, you might come to me and ask me for a shovel. The reason you ask me for a shovel is because a shovel makes the process of digging much easier. A catalyst works in the same way. A catalyst makes a reaction much easier to accomplish, and so it speeds it up by giving it a bit of a kickstart. but it does not actually get utilized. So when you're digging a hole, hopefully you're not actually using up your shovel. All right, you should be able to use that shovel over and over and over again without having to replace it. The catalyst works the same way. So thinking about what this sign means here, we have a few things. All right, maybe pause the video and try and see if you can figure out what this means, and then I'll go over it here in just a second. Okay, so the 100 degrees there indicates that it should be at 100 degrees Celsius when you take on this reaction. The PT here, that's platinum, all right, and that means that platinum is a catalyst. We have two arrows here, which means it's reversible, but the forward arrow is greater, which means that it is product favored. Okay, so that's basically all the parts there to that. The next thing here we have is some symbols that fall inside chemical reactions, oftentimes to indicate the state of matter that things are. So you can see an S or a CR when something is solid, or a reactant or a product is solid. And the CR just stands for crystalline solid, or a crystalline form. And so sometimes you see an S or a CR in there, although S is a lot more common. This next thing is a cursive L, all right, which indicates that something is a liquid if you see it in a chemical reaction. If it has a gas there, or sorry, if it has a G there, that indicates that it is a gas. All right. And here I just take a second to mention that there are 7 diatomic elements. All right. Oftentimes these are gases, so like hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, things like that. Technically, bromine and iodine are not gases. Bromine is a liquid, and iodine tends to be a solid at room temperature. But we remember these as the 7 diatomic elements. All right. And I have a mnemonic for that. I say Honkelbrief, H-O-N-C-L-B-R-I-F, Honkelbrief, and I don't know, it's this sort of nonsense word that I use to remember the 7 different diatomic elements. The last thing here is AQ. AQ is one that you probably have not come across too much. It means aqueous. All right, aqueous has the prefix similar sort of to aqua, which is related to water, and so hopefully you can remember that aqueous means that a substance is dissolved in water. Okay, and so for instance, if I gave you NaCl aqueous here, that's salt, sodium chloride, normal salt that is dissolved in water, so NaCl aqueous would just be salt water. Sometimes things need to be aqueous for the reaction to get going, and so for instance here I give you a reaction. Try and think about what this would be. Again, maybe you should pause the video and try and interpret what's going on in this reaction, and then in 1 second I'll just go ahead and explain what's going on. All right, so this has solid zinc, which normally we just call like zinc metal. All right, it's reacting with aqueous hydrochloric acid, so dissolved in water. All right, when you mix those together, you should warm it lightly, which is what the delta means. All right, and the products that are going to be formed with this reaction are hydrogen gas, H2 gas, and zinc chloride, which remains aqueous, which remains dissolved in water. So that's kind of what that means here. You can take a second to read over that if you like. All right, the next thing I'm going to talk about is different types of reactions. There are 5 types that I'll talk about here. There are actually other types, but I'm going to summarize kind of the main ones here. So the main types here are synthesis reactions. Synthesis means that you're making something. That's what synthesis means. Like photosynthesis, you make energy out of sunlight, or technically speaking, really you make starches, which are carbohydrates, by using the sunlight. So photosynthesis, you're making something there. Synthesis reactions, you make something. The way that you make it is by joining 2 other things together. All right. The big deal here is there's only ever one thing on the product side of the equation. And so this gives an example like maybe you take substance A and you combine it with substance B and it forms this compound AB together. Or I give you a real-life example here. We've got hydrogen and oxygen gas combining to form water. All right, and so you just have one product on both of these sides. You can technically have a compound combining with another compound to make one thing together, and that's also a synthesis reaction. So the big thing here is that there's only one product on a synthesis reaction. The next thing we have is a single displacement reaction. The single displacement reactions we have a compound and an element reacting together. What happens is the element comes in and it replaces an element inside of the compound. Metals replace metals typically, although hydrogen in this case kind of counts as a metal. Hydrogen tends to replace metals. Metals tend to replace hydrogen. But the general rule of thumb is that if a metal comes in, it's going to replace another metal. If a non-metal comes in, it's going to replace another non-metal. So I'll give you an example of each of these. Fluorine is the element that comes in here. Fluorine is going to replace the chlorine in this substance because those are both nonmetals. And so the elemental fluorine comes in and it replaces chlorine in the substance there. An example where a metal replaces a metal is when lithium is coming in here and it replaces the sodium in that compound, all right, and we get lithium chloride and sodium is displaced. Double displacement occurs when you have two compounds reacting together, and what happens is the metals on those compounds switch places. All right, so or you could consider it the non-metal switching places other way, but for instance here we've got sodium and silver kind of switching partners here and ending up with the other thing there. So that's how a double displacement works. These tend to look very complicated when you're looking at them. There's lots of different elements in them, and we've got a compound plus a compound, and we get two compounds in the end as well. So that's how a double displacement works. Decomposition, we have a reactant we have one compound as a reactant, and that compound breaks down to form two other compounds or some elements sometimes. And so in this case, how you know that you've got a decomposition reaction is there's only one reactant involved. All right, for instance, I give you here a decomposition reaction of water. If you run an electrical current through water, you can get it to decompose into hydrogen and oxygen gas. And so it runs the reverse of the synthesis process. Decomposition is kind of the opposite of synthesis. We've got one thing in decomposition, one reactant breaking down into multiple other things. And then the last kind of reaction we have here is a combustion reaction. Combustion reactions involve what we call hydrocarbons. Hydrocarbons are just elements that have carbon and hydrogen in them. All right, and so what happens here, I've given you some examples actually here of hydrocarbons. C6H14, that's 6 carbons, 14 hydrogens. Or C4H8, that's a hydrocarbon. It can be really, really big though, so I give you an example here. C128H250, that is also a hydrocarbon. And so things like that, just as examples. And so the product of a combustion reaction, which I should have mentioned up here above, combustion is just burning a fuel in the presence of oxygen. That's what combustion is. It's literally just burning something, all right? And so there can be different fuels that you might have. For instance, you can burn wood or you can burn gasoline or various other things. But what you end up getting here is you get a hydrocarbon and it's burning in the presence of oxygen. So oxygen comes in as a reactant. It always forms carbon dioxide and water. The only thing that really changes here is the fuel, the CXHY. And I'll tell you, actually, sometimes that fuel even has oxygens in it. So for instance, ethanol has oxygen in it, and it acts as the fuel. So sometimes in the hydrocarbon fuel, sometimes you'll see an oxygen in there as well, and that's okay. But it reacts with O2 gas, and it forms carbon dioxide and water. So that's a combustion reaction. Here, identifying different reaction types. We're going to go through and just do some practice of this. So look through these, maybe pause at each section or something along those lines and try and figure out what it is as I go through them and try and predict what sort of reaction we have in each of these. So for this one, NaCl plus AgNO3 yields NaNO3 and HgCl. You should see here we've got a couple of compounds reacting together. They make a couple of other compounds. What's really happening is like the silver and the sodium are switching partners here. And if that happens then, it's a double displacement. Okay, the compounds are just kind of switching what's in front, and that's called a double displacement reaction. On this one, we've got just one product here, all right? These two things are coming together to form CaSO3. If two things combine together to form one thing, that is called a synthesis reaction, all right? Only one product in a synthesis reaction. This next one here, we've got carbon and hydrogen, hydrocarbon here. It's reacting with oxygen. It forms carbon dioxide and water. that is a pretty clear combustion reaction, all right? Hydrocarbons plus oxygen yield carbon dioxide and water. This one, zinc plus HCl yields zinc chloride and hydrogen gas. In this one, the zinc is a metal. It's coming in, it's displacing the hydrogen, all right? It's an element displacing an element in another substance. That's called a single displacement reaction. It's different here because we have an element coming in and an element leaving in the end. So this zinc just displaces the hydrogen as opposed to the double displacement where you have two compounds and they start out two compounds, they end up two compounds, they just switch what's in front. Here you've got an element coming in, it's replacing something inside of a compound, and then another element is leaving on its own. All right, on this one we have just one reactant, and that reactant is breaking down to form a couple other things. That is a decomposition reaction, if you've got one thing breaking down into two other things. On this one, iron and sulfur coming together to form iron 2 sulfide. All right, if you've got two things coming together to form one thing, that is a synthesis reaction. All right, this last one here, we've got one thing, it's breaking down into a couple other things. If something's breaking down, that's decomposition. If we've got just one reactant, that's decomposition. Another one here, we've got copper coming in here, that's an element. It replaces silver in this substance, and so what we end up here with is single displacement. An element replaces another element inside of a compound. This one, hydrocarbon and oxygen yielding carbon dioxide and water. All right, so that hopefully should be something that clearly steps out as a combustion reaction for you. And then this last one, AlNO33. This one looks very complicated. It's a compound, and we have another compound, and they kind of switch what's in front. The aluminum ends up with hydroxide. The sodium ends up with nitrate. All right, and so that is a double displacement reaction. Okay, so that is it for this set of notes. There will be another video that's posted on balancing chemical equations and going through some examples from that. So if you're looking for the notes on balancing, that will be posted in another video. If you have any questions on any of the concepts in this video, make sure that you stop in and ask.